Great. So I think everyone is trying to attempt it. That means everyone is clear about what it is, like what the question is trying to ask. Completely fine. So let's check like what is the right answer for this. So what I have done, I have written out all the possibilities that could be there for these three students, S1, S2, S3. Okay. If you will closely look at it, most of you have studied digital logic in third or fourth semester, right? And this table looks a lot like a truth table. If we replace G and B by 1 and 0, it looks a lot like truth tables that we have seen in digital logic. Okay. Again, here we have three variables. Each of them can have two values, either a girl or a boy, right? So from that, let's calculate what the probability will be. So for B1, the event is that there is only one boy. So from all these, just check where to get one boy. So there is this one event where we have one boy, and there is this again second sample where we have one boy. This sample also we have one boy. So out of total 8 samples, we have 3 samples where we are getting a single boy, right? So the right answer for B1 is 3 by 8. Okay. How many of you got this answer? 3 by 8? Fine. Let's go ahead for this event C. What is this event? It says events that girls are more than boys. So let's try to see. Here the girls are less. Here the girls are more than boys. So 1, 2, 3, and 4. So in 4 cases out of total 8 cases, we have girls more than boys. That means the probability is 1 by 2, right? Or have I missed any of the cases? I don't think. So these are the probabilities that we are getting. For B1, the probability is 3 by 8, and for C, we are getting probability 1 by 2. Is it clear? Anyone who couldn't understand this, or is there any doubt? Great. Let's move ahead. So with that, we'll study some more like concepts related to probability. So first, the probability of happening of an event plus here plus denotes union again, as I said earlier. The probability of happening of an event A plus or the union of the probability of happening of of probability of not happening of that event A. If you will sum that, that is 1. Why? Because the probability of happening of A is this area divided by the complete area, obviously. That is what probability is. And the probability of not happening of the A is this area, this outer area. So if we'll add these two areas, this one and this one, then what will happen? It will be equal to this complete area of sigma. And when you will divide this complete area by the area of sigma, what will happen? You will get 1. So that is how we can visualize these relationships. Next, we have probability of A minus B. That means probability of uh, all those cases where A is happening but B is not happening. So how is this possible that for the same sample space there could be two events? Is like this. So here the sample space was same. What we did? We did an experiment for 3 times and we defined two events over that. So that is this case. So we have a certain sample space, and within that sample space, there could be two different events based on the definition of those events. In such a case, we are trying to identify those elements such that if those samples agree to the conditions of A, they should not agree to the conditions of B. All right. So what does this mean? That we want to get this area. Not the complete area of A, only that area where there is no common area with B. All right, and this common area we call it A intersection B. That is what we studied it. So if you can see, you can clearly identify that. How we can identify is we can calculate PA and then subtract intersection from it, and then you will get this area. Okay. Next, there's this relation BA union B, which is the complete this complete area. This one as well as the B's area. All right. How will we find that? If we clearly sum up PA and PB, what will happen is that this common area added two times, one from the side of A and once from the side of B. All right. So we'll subtract just one instance of that, and that way we will get union of A and B. So that is how we can visualize these relations using a Venn diagram. I will not be doing this visualization exercise for all the relations, but I am just trying or helping you to develop that intuition that it is not always mandatory for us to learn or I can say by heart these relations, by heart these formulas. You can say we can also like intuitively try to identify them using such Venn diagrams. Now we are talking about independence of events. So let's say if there are two events A and B, let me clear this again. Okay. So let's say if there are two events A and B, they are like this right now. Let me take another case for a moment, that this is A and this is B. So can I say that if there is a sample which is in A, then it is definitely not in B. Is that true?
Yes, sir.
Yes.
Yes, sir.
Where A and B are like these. This is A and this is B. Now can I say that if there is a sample in B, it is definitely in A?
Sir.
Yes.
Yes, sir.
Such a case, in a case like this, for any sample in A, can I guarantee its inclusion or exclusion from B?
No, sir.
We cannot do that, right?
No, sir. No.
Right? Because the sample could be here as well as the sample could be here. If the sample is here, it is not in B. But if the sample is here, it is inside B. So such events are said to be what I can say. So I cannot tell much about these events right from here, but from these diagrams, I can say that these events are dependent on each other. Why? Because if I take a sample from one of the sets, I can define its inclusion or exclusion from the other event. All right. In such cases, we can say that these variables are independent, or rather, these events are dependent events. One will happen, other will also happen. If something is in A, then it is not in B. If something is in B, it is not in A. And in this case, otherwise, right? But in such cases, we cannot say anything about them. So we consider that they may be dependent or they may be independent. All right. But in terms of these operations, union, intersection, or any similar operations, we cannot tell anything about dependence of these events. However, we can tell about the independence of events. So, what is the independence? That if the probability of A intersection B, so those elements in our sample space which lie in A as well as B, if that probability is equal to happening of A as well as B, sorry, either of A or B, sorry, I said it incorrectly. That will mean that this what this expression means is it is just nothing but a dot operation between A and this probability of A and probability of B. Not exactly a dot operation, it is exactly a multiplication, but you can visualize it that way. That probability of A as well as probability of B multiplied together. So that will mean that independently A also happens and B also happens. So if this expression is true, we can say that our events are independent. So we do not need to go very much into the depth of independence events, because what we are more concerned towards when we are talking about inference and learning is dependent events, because independent events are not useful to us. If two events are completely independent, we cannot define a relationship between those events, and that way we cannot derive any inference based on the properties of those events. All right, and that is why we are not much interested into these ones. So we'll just for now we'll just understand that if this condition is true, the events are independent. Okay, and we'll move forward.